Okay, in this video I'm going to talk a little bit about graphing. It's going to be an introduction. And because it's an introduction, I'm just going to go through some definitions first. I would like to talk about what's an axis. Axes is the plural. What are coordinates? What are the quadrants? What are linear equations? There's three of them. You can see them over here, the slope-intercept form, standard form, point-slope form. And then I'm going to end up with what's called the slope formula. Now, in order to talk about graphing, we probably should ask ourselves a couple basic questions even before we get to definitions. And that, first of all, is where does it come from? How did we come up with this whole idea about graphing? So where did graphs come from? And I'm going to tell you a story that I learned way back when. Now, I don't know how exactly truthful this story is, but it sure sounded pretty plausible to me. So I'm going to relay it to you guys. Graphs, if you remember, are also called Cartesian graphs or Cartesian coordinates. Now that's one of the definitions that we're going to look at, but I wanted to say this right off the bat because of this word right here, cart, or Cartesian. The story goes that there was a French mathematician whose name was René Descartes, hence Cartesian coordinates. And the story that I heard was that he was sick in bed one day, and he was looking up on the ceiling, and he noticed that there was this spider crawling across the ceiling, kind of an erratic pattern, maybe something like this. And being the mathematician that he was, he said, well, how could I describe the pathway that spider is taking? And so he was thinking that, if this spider stayed just on this little number line, I would be able to describe it pretty easily, right? So, for example, here's 0 right here. If it was going in the positive direction, I could say it was moved over 1, 2, 3, 4, however many spaces to the right. If it was going in the opposite direction, -1, -2, -3, -4, however many points in the left, he said, but what if I did this? And this is where the aha moment came in. He said, what if I took this graph, this number line, and flipped it up to 90 degrees and intersected it like this? Kind of a simple idea, right? And he said, then what I could do is I could not only describe the spider on this point here, but I could also describe his pathway this way as well. Let's go, aha, so what can I do with that? And all of a sudden all these ideas started to develop. He said, we'll call this particular number line the x-axis. Okay? And then we'll call this number line that we moved at 90 degrees also in, positive direction was this way. Negative direction was this way. So just take it and just moved it like this. We'll call this the y-axis. And to describe where the spider started, what he says you can do is you can use basically two of these points. You can use an x point and a y point. So for example, where did it start off? It started off right there. You could say it started off 2 along the x, and then you had to go 1, 2, that's a 3 there, 4 there. Look, I'll call that 5 just to make it easy. And looks like 5 along the y in the positive direction. He called this point, this ordered pair, 2, 5, and again it's also called an ordered pair, or it's also called coordinates. 2x, 2 for the x, and 5 was for the y, so he called those coordinates. And then he said, then you could say it moved to the left to 1, 5, then it moved down to looks like 1, 3, and then it moved over to like -2, +3, that sort of thing. In other words, you could trace where this was going by just a series of coordinates. All right? So, kind of interesting. Let's move on a little bit. He said you'll also notice that the x and the y axis created 4 different spaces, right? So he's noticing some patterns that occurred there. He called these individual spaces quadrants, okay? And this first upper right-hand space he called quadrant number 1. And he noticed that the x value in quadrant number 1 was a positive number, and that the y value was also a positive number. So you could identify where your point was located just by looking at the x and y values in the ordered pair. He called this quadrant the second quadrant, this quadrant the third quadrant, this quadrant the fourth. So you'll notice that it goes like in a big C, doesn't it? From up here, and just make like a big C. So 1, 2, 3, 4. And again, he tried to do the same pattern. For example, what's the x and the y value in the second quadrant? Well, the x value is negative. The y value is positive because you're going up. In the third quadrant, the x value is negative. The y value is negative. So your coordinates would be both negative numbers. In the fourth quadrant, your x value again is positive, and then your y value is negative, so your coordinates would have a positive then a negative number. And so you could identify again where it was located simply by looking at the coordinates. All right, let's move on just a little bit. Now, again, let's go to a xy axis. And this is also called a Cartesian graph. And the xy are called Cartesian coordinates, or just coordinates. It's probably a good idea to label the axes, even though we know that's x and that's y, just as a matter of keeping things in order. The other thing that he noticed was he started developing this really cool system. He goes, what if, let's just do the point positive 2, positive 1. So the coordinate is 2, 1, and there's my point there. And let's do another point. Let's just go all the way over here. Let's go negative 1, negative 2, negative 3, and then negative 1, negative 2, negative 3, negative 4. So we'll do this point down here, negative 3 along the x, negative 4 along the y. And if I connected those 2 points and extended the line, and I'll just put arrows there to say just indicate that it's going on forever, I now have created what's called a linear equation. What's so important about a linear equation? Well, in a linear equation, you've got an x value and you've got a y value. So in linear equations, you now have 2 variables that you can use to solve for an answer. So instead of, whereas before I could only solve for like one variable, something like 2x is equal to 6, divide, use your math, divide by 2, so x was equal to 3. I only had one variable, so I'd only have like one number line. I could only locate the answer on that, on that one number line. But now with a linear equation, I've got 2 variables. And I'm able to locate the answer as a line because I have 2 axes. So each variable basically represents another axis, right? Now, the cool thing about linear equations is not only did we increase our number of variables, but we also have different forms of the lines that we could talk about. Now, the 3 types of lines that we're going to be interested in are called the slope-intercept form, and the slope-intercept form looks like this. You'd say y, you solve for the y, and then you say it's equal to mx plus b. Now, what does that mean? Well, the m stands for something called a slope. The b stands for where the line intersects the y-axis. Intersects the y-axis. This is a really popular form of, I'm sorry, that was off the line there. This is a really popular form of a linear equation that a lot of students learn. The second type of equation or form that we want to learn is something called the standard form. And the standard form follows the equation a times x plus b times y is equal to something called c. In other words, the x and the y are on the same side. We'll talk about some of the advantages of that later on. And then something finally called the point slope form. And the point slope form looks like this. You'd say y minus y sub 1, so these are two different y's, is equal to m times x minus x sub 1. Those are two different x's. And the x1 and the y1 go together as one coordinate, and then this x and y are another coordinate. And the m, again, is the slope. So these three forms of the equations I'm going to save for another video. But the last thing I want to end off with in this little introduction is what's called the slope formula. Now, what is the slope formula? The slope formula says this, that the slope is equal to the rise over the run. Another way of saying rise over run is the difference between the y values over the difference between the x values. These little triangles, those are called deltas. It's a Greek letter, and it means change. All right, so the change in y over the change in x, or the more exact formula would be this, y1 minus y2 over x1 minus x2. And these are just like sets of points or coordinates on the line. Now, let's look at this particular line and see if we can figure out what its slope is. All right? So, the slope of this line, the one that's going up, would be equal to, we said, the rise over the run. So what you do is you start at any point, and then you go up to the next point. Now the slope here would be the difference between the two y values, so negative 4, there's one y, minus negative 1, or just 1 rather, over the difference in the x values, so negative 3 minus 2. If I were to work this out mathematically, I would get negative 5 over negative 5, which is equal to a slope of 1. Now what does that tell me? Remember we said it was rise over 1. So if I go up 1 and over 1, I'd be right on the line. If I go up 1 over 1, right on the line, up 1 over 1, up 1 over 1, up 1 over 1. And I would end up at 2, 1. Sure enough, that's where I ended up. So the slope of this line would be positive 1, and that's how you figure it out here. I can take that and put the m in here. Let's do that. Since I know my slope is equal to 1, I can now put this into one of these three equations to figure out what the equation for this linear line is. Let me show you what I would do. I would probably put it into y minus y1 is equal to m times x minus x1. Remember, that's called the point slope form. Why would I use this one? Well, I happen to know what one of the points are. For example, 2, 1 is one of the points. So I'm going to call the x value as 2, the y value is 1, so I'm going to put both of those, replace them. I know that my slope was equal to 1, and I don't know what any other x is, and I don't know any other y. So the equation in point slope form would be y minus 1 is equal to 1 times x minus 2. And this would be the point slope form for the line that I drew here. Now you might be asking, what if I put in negative 3, negative 4? Well, let me show you what happens when I do that. Let's go over here. Y minus, the y value again is negative 4. The slope we said was 1. The x was, again, remember, we don't replace this x and this y. Only the ones that have the subscripts are the ones that we replace. But we said that it would be negative 3, so minus negative 3. So what we're claiming is that this equation should be the same as this equation. Is that true? Let's figure it out. Well, let me see. I know that y minus a negative is like saying plus, so I'll say plus 4. This is step 2. I'll go ahead and do the same thing here. 1 times x minus a negative makes that a plus. When I distribute that 1, I just get x plus 3. 1x plus 3. Y plus 4. And now I'm just going to solve for y. So let's move the 4 over here. Let's subtract it. And you get y is equal to x minus 1. Okay? Do you recognize that form? That's the slope-intercept form. Now, if we work this one out, we should get the same equation. Let's see if that's true. So I distribute the 1. Let me go ahead and add 1 to both sides. Oh, sure enough, look at that. It turns out to be the exact same equation. So what's the point? I can use any point on the line, and it will give me, in the point-slope form, and it will give me the equation that will be true for any point on this line. The other thing is, you notice I changed the point-slope form to the slope-intercept form. And remember what we said about this value here, this -1? We said -1 should represent where the line crosses the y-axis. Look at that, at -1, where y is -1. So it does work. Now that was an awful lot of information to throw at you, but hopefully you'll be able to play this a couple of times and you should be able to understand what happened. Okay? I hope this was helpful.